Let's now move from roadmap to reality. Our next session showcases Pasqal's progress in action. Let's welcome Pasqal CTO, Loïc Henriet, who will walk us through the major milestones defining this year.
This presentation is about progress, measurable progress on our roadmap. We've heard about all the technical milestones that we've hit over the past 2 years, and I want to zoom out, take a step back, and present those milestones in the context of our roadmap and where we're going. As we heard about today, we are witnessing now a change in the quantum ecosystem, from noisy prototypes to real-world applications. To really scale those real-world applications, what we need is 3 things. First one is scale. Second one is reliability. And third one is practical use cases. And today, I'll show how we continue to progress along those 3 lines with 3 specific results. 1,000 qubits that were realized on our QPUs, logical computation, and solving differential equations using logical qubits, and finally, achieving quantum advantage in material science. This means a lot for Pasqal and for the entire ecosystem. This is entirely aligned with what we had planned 2 years ago, and it helps us underline what we need to do next. First, about scaling to 1,000 qubits. So this is the baseline that we were at in 2024. So we had achieved 1,100 atoms trapped, but without rearrangement, the crucial step that we heard about several times today, like moving the atoms to form a specific pattern. So what we had was a system that was capable of scaling, but not yet fully optimized. This is what we reached this year. So at the core of our system is a vacuum chamber, where we trap and control our qubits. Over the past year, we've been working on a new design, and most importantly, we've delivered on this design that you can see here on the left part of the screen. And in collaboration with the CNRS, we implemented rearrangement algorithms with several cycles. So after 1 cycle, we take an image, measure the number of defects, rearrange again to be able to reach 1,000 atoms without any defects. With this novel generation platform, we were able to scale the lifetime of the atoms in the tweezers and to really demonstrate what it meant to scale in our QPUs. This is the final image, so from initial charging of the array of atoms to fully rearranging the total register. This capability can be directly transferred in our industrial machines. So what we are doing here is very deliberate. So this is R&D that prepares for the future towards 10,000 qubits, while at the same time delivering immediate performance gains for our production machines. But scale alone is not the end goal. Having more qubits is only useful if you have reliable qubits. You can use them with confidence and really reliably. For digital quantum computing, what this means is quantum error correction. That's what we have achieved this year. And we've managed to solve differential equations using logical qubits. To implement logical qubits, we introduced a zoning architecture. This is something that is enabled by the nature of neutral atoms that we can move around during the computation. This was demonstrated here in Paris for the first time, already some time ago by Antoine Brouès and his team, and this is at the core of the future of neutral atom technologies, quantum error-corrected QPUs. This allows us to define a computation zone where we implement gates, loading zone for a reservoir of qubits, and a storage zone with a given quantum state embedded in them before using them again for computation. So we can isolate operations, apply gates only where we need it, and we can scale operations efficiently. So with this architecture, we tackled one of the most fundamental problems in science and industry, which is solving differential equations. These equations are everywhere. They describe how heat diffuses in materials, how fluids flow in aerodynamics, also how financial products are priced. And in fact, a large part of modern industry relies directly or indirectly on solving differential equations. So that's what we've done. We've taken a real problem and an end-to-end approach, from the application to the logical and physical qubits. It's really a practical computation directly connected to real-world applications. So the key result is simple and powerful. We reach a lower error with logical qubits than what we had with physical qubits. So we believe that this is the first time worldwide that differential equations can be solved using a logical quantum algorithm. And what we find is actually that logical encoding helps in solving the equation. What you can see on the bottom right plot is actually the target differential equation that we want to solve. And you can see the results with both physical qubits and logical qubits. As you can see, the logical encoding gives rise to far better performances. So it's a major result with many applications in the long term in energy systems, fluid dynamics, materials modeling, financial simulation. Now, it's important to be clear. We are not yet at a stage where we have quantum advantage for these particular problems. We need to scale them in the future, and that's what we will do. But this result shows something fundamental, that we can really measure progress on our hardware on a measurable outcome of a real-world use case already on logical qubits right now in 2026. And the next question is, okay, but where can we reach the quantum advantage first? Well, the answer is in physics-driven problem, as we saw earlier. And that's also what we did in 2025 and 2026. We started from theory. We identified regimes where classical simulation would fail. This was a plot that we showed 2 years ago at the Pasqal Thoughts event, just pinpointing where we would be able to demonstrate quantum advantage. And we used this exact analysis, to actually carry out our quantum advantage experiments. And we applied that to real material, TMGO, that you saw earlier today. So the workflow is measure experimentally the material, simulate it on the QPU, and then compare the results, and then go beyond what can be done with the classical numerics. And we obtain results in a few hours that we believe would take more than 2 weeks on the most powerful supercomputers in the world. And even then, we would not have convergence guarantees. We were talking about reliability earlier. You show this image. Everywhere on the planet, we get this advantage. We got it in Massy twice. We got it in Canada and at CEA and in Germany at Jülich Supercomputing Center. So regarding quantum materials, we have demonstrated something quite powerful, but we need to take it to the next stage. And to take it to the next stage, we really want to place neutral atoms at the center of advanced simulation capabilities for material science. Integrate it into hybrid workflows using GPUs, CPUs, and QPUs for material discovery in a closed loop. And we'll be able with that to enhance computational pipelines in key sectors that are related to material science. So here we're talking about discovering new sensors for magnetic field, electric fields, new memory devices with spintronics. We're talking about optimizing batteries, solid state, lithium-ion. So this is really something quite powerful. This is the roadmap that I showed 2 years ago, and this is what we achieved. On time or in advance, 1,000 qubits, zoning architecture, multiple logical qubits. We've released our Orion Gamma machine, and we are in the process of installing it in Saudi Arabia and at Cineca in Italy. We have achieved quantum advantage on quantum matter. This is a prediction that we did like 2 years ago. We would achieve quantum advantage on quantum matter between 25 and 26. And we did it. So to conclude, we are scaling system. We are increasing reliability with error correction and with devices that reproduce the same results consistently, reliably all across the world. and we have achieved quantum advantage with practical use case. Thank you very much.